What if a visitor from another star system is trying to tell us something? What if the glowing ball of ice and rock hurtling through our solar system isn't just a comet, but a messenger carrying secrets about the death of alien worlds? Tonight, we venture into the frozen darkness between stars, where our comfortable understanding of celestial mechanics crumbles and the impossible becomes uncomfortably real. Its name is 3I Atlas, and it's doing something no comet in recorded history has ever done. Not in the thousands of years we've watched the skies, not in the decades since we've pointed our most sophisticated instruments toward the cosmos. Something unprecedented, something that makes even seasoned astronomers pause their calculations and whisper to each other in conference rooms and late-night emails. Are we seeing this correctly? Picture this, a chunk of primordial material, older than our sun, torn from a solar system light years away. It's been drifting through the absolute zero of interstellar space for potentially millions of years. And now, as it passes through our cosmic neighborhood, warming under our sun's rays for the first time in its existence, it's releasing something that shouldn't be there, something that makes no sense, something that forces us to reconsider everything we thought we knew about the chemistry of alien star systems. The comet glows not just with the familiar cyan blue of sublimating water ice or the warm yellows of dust reflecting sunlight. No, 3I Atlas is emitting a chemical signature so unusual, so alien, that when the detection was first made, researchers thought their instruments had malfunctioned. They checked their calibrations. They compared notes across multiple observatories. They ran the analysis again and again. The result didn't change. What if this comet is showing us the chemical fingerprint of a solar system that died before Earth even formed? What if its composition reveals catastrophic events in a stellar neighborhood we can barely imagine? What if? And here's where speculation becomes almost terrifying. What if this comet's strange behavior is evidence of something artificial, something designed, something that was meant to travel between stars? I can already hear the skeptics, and they're right to be skeptical. Extraordinary claims require extraordinary evidence. But here's what makes this different from the usual clickbait speculation. The evidence is real. The chemical detections are confirmed. Multiple independent teams have verified the findings. The question isn't whether 3I Atlas is doing something unprecedented. It absolutely is. The question is what that something means, and whether our current understanding of cometary science is adequate to explain it. This is the story of 3I Atlas, the second confirmed interstellar visitor to our solar system, and the first one to completely upend our expectations. It's a story that begins with discovery, moves through confirmation and wonder, and ends in a place where science meets speculation at the edges of what we can know. Along the way, we'll explore not just this enigmatic visitor, but what it tells us about the universe beyond our small corner of space. So settle in, turn off the lights if you dare. Because tonight, we're going to follow this cosmic wanderer into speculative territory that's both thrilling and scientifically grounded, asking questions that might not have comfortable answers. Before we dive deeper into this fascinating and unprecedented story, if you're intrigued by interstellar visitors, cosmic mysteries, and the strange objects that drift between the stars, make sure to hit that subscribe button and ring the notification bell. Drop a comment below telling me what time it is where you're watching from and where you're located. I love seeing our global community come together to explore these cosmic questions. And if you appreciate the research that goes into these deep dives, really helps the channel grow. Your engagement tells YouTube to share this with more people who crave substantive space content. Now let's continue our journey with 3I Atlas. Let's address the elephant in the room immediately. Is this thing going to hit us? The answer is an emphatic, unqualified, mathematically certain no. 3I Atlas poses absolutely zero threat to Earth, and I want to make that crystal clear before we venture into the speculative territory ahead. The comet's trajectory has been calculated with extraordinary precision by multiple space agencies, and there is no possibility, not even a remote one, of impact with our planet. When 3I Atlas was first detected on January 6, 2025 by the Atlas survey system in Hawaii, astronomers immediately began plotting its orbit. Within days, they had enough data points to construct its path through our solar system with remarkable accuracy. The comet will make its closest approach to Earth at a distance of approximately 180 million kilometers, that's about 112 million miles, or roughly 1.2 times the distance between Earth and the Sun. To put this in perspective, when Mars is at its closest approach to Earth during favorable oppositions, it comes within about 55 million kilometers. 3I Atlas will never get anywhere close to even that distance. The Moon orbits Earth at an average distance of about 384,000 kilometers. 3I Atlas will pass us at a distance more than 468 times greater than the Moon's orbit. It's not coming anywhere near us. NASA's Center for Near-Earth Object Studies, which maintains constant vigilance for potentially hazardous asteroids and comets, has confirmed that 3I Atlas presents no danger. The European Space Agency's Space Situational Awareness Program concurs. The Minor Planet Center, which coordinates observations of comets and asteroids worldwide, has verified the trajectory. Every credible space agency that's examined this object agrees we're safe. But here's what makes this safety even more assured. 3I Atlas is on what astronomers call an unbound orbit. Unlike the periodic comets that loop around our Sun in elliptical orbits, returning again and again over centuries or millennia, 3I Atlas is passing through our solar system just once. It came from interstellar space, it's swooping around our Sun, and it's heading back out into the cosmic void. It's not staying. It will never return. The comet reached perihelion, its closest point to the Sun, on May 28, 2025, coming within about 0.65 astronomical units of our star. That's about 97 million kilometers, or roughly the distance at which Venus orbits. At this distance, the Sun's heat began to warm the ancient ice, causing it to sublimate and creating the comet's characteristic tail. This was when observations became most intense, when the unusual chemical signature was detected, and when astronomers around the world trained their instruments on this visitor from beyond. Now, in October 2025, 3I Atlas is already heading outward, cooling as it travels, its activity diminishing as the Sun's warmth fades behind it. Within a few years, it will cross the orbit of Neptune, passing beyond the realm of the gas giants. In a few decades, it will reach the Kuiper Belt, that distant region of icy bodies beyond the planets, and then it will continue outward into the Oort cloud and beyond, returning to the darkness between stars from which it came. So no, 3I Atlas will not hit us. It will not rain down fire from the heavens. It poses no threat to satellites, spacecraft, or the International Space Station. The danger, if we can call it that, is not physical, it's conceptual. Despite these reassuring facts, what shadows might lurk in the implications of what this comet is revealing? What does it mean that an object from another stellar system is displaying chemistry we've never seen before? And if 3I Atlas is representative of material from its home star system, what does that tell us about the diversity and perhaps the dangers of worlds beyond our own? Let's talk about what 3I Atlas actually is in concrete, measurable terms, because before we can speculate about what makes it unprecedented, we need to understand the sheer scale and characteristics of this object. The comet's nucleus, the solid core of ice and rock at its heart, is estimated to be between 1.5 and 3 kilometers in diameter. That's roughly a mile to 2 miles across. Picture a small mountain, or about 15 to 30 football stadiums, lined up end to end. Now imagine that mountain is made of ancient ice, rock, and frozen gases that formed in another solar system around another star, potentially billions of years ago, At its brightest, as it rounded the Sun during perihelion, 3I Atlas reached an apparent magnitude of around 8.5, too faint to see with the naked eye, but easily visible through modest backyard telescopes. Thousands of amateur astronomers captured images of this interstellar visitor, contributing their observations to the global database that professional astronomers use to refine their understanding of the comet's properties. But it's the speed that truly staggers. When 3I Atlas entered our solar system, it was traveling at approximately 35 kilometers per second relative to the Sun. That's 126,000 kilometers per hour, or about 78,000 miles per hour. To put this in perspective, the fastest rifle bullet travels at around 1.2 kilometers per second. This comet was moving 30 times faster than that. The International Space Station orbits Earth at about 7.7 kilometers per second. 3I Atlas was moving more than 4 times faster. This velocity tells us something profound. 3I Atlas is not gravitationally bound to our Sun. Its speed exceeds the solar system's escape velocity at its current location. It has enough kinetic energy to break free of the Sun's gravitational pull and return to interstellar space. The mathematics are unambiguous. This object came from somewhere else and it's going somewhere else. Astronomers have attempted to backtrack its trajectory to determine where it came from. The calculations are complex, fraught with uncertainty, because even tiny gravitational perturbations from passing stars over millions of years can dramatically alter a comet's path. But the best estimates suggest that 3I Atlas has been wandering the galaxy for at least several million years, possibly much longer. It could be 10 million years old, it could be 100 million. It might have formed when dinosaurs walked the Earth, or even earlier, in the time before multicellular life emerged in our oceans. During its time in the interstellar medium, 3I Atlas existed in conditions almost incomprehensible to human experience. The temperature of deep space, far from any star, is around 2.7 Kelvin, just 2.7 degrees above absolute zero, the coldest possible temperature in the universe. At these temperatures, chemistry essentially stops. Molecules don't react. Change happens over geological, even astronomical timescales. The comet's composition reflects this ancient origin. Spectroscopic analysis, the study of the light it reflects and emits, reveals a mixture of water ice, carbon monoxide, carbon dioxide, and various organic compounds. This is similar to what we see in comets born in our own solar system, which isn't surprising. The laws of chemistry are universal. The same elements exist everywhere, and they combine in similar ways. But here's where the numbers become genuinely strange. When 3I Atlas began to warm as it approached our Sun, instruments detected the emission of certain molecules in quantities that don't match any comet we've ever studied. The ratio of carbon monoxide to water vapor is approximately 3.5 times higher than we see in typical solar system comets. The abundance of certain complex organic molecules is off the charts. And there's something else, something we'll explore in detail shortly, that makes absolutely no sense according to our current understanding of cometary formation. The uncertainty in these measurements is real. Cometary composition can vary significantly across the surface of the nucleus, and we're observing 3I Atlas from a distance of over 100 million kilometers. Our instruments, sophisticated as they are, can only tell us so much. But multiple independent observations from different facilities all point to the same conclusion. This is not a typical comet. But what if these numbers hide something more than just unusual chemistry? What if the compositional anomalies are trying to tell us a story about the stellar system from which 3I Atlas was ejected? A story that might be darker and more catastrophic than we're comfortable imagining. Here's where our story takes a turn into genuine scientific mystery. Because what makes 3I Atlas truly unprecedented isn't its size, its speed, or even its interstellar origin. It's what the comet is releasing as it warms. Among the gases sublimating from the comet's nucleus, spectroscopic analysis has detected significant quantities of hydrogen cyanide, HCN. This by itself is not unusual. Many comets emit hydrogen cyanide. It's a simple molecule, just one hydrogen atom bonded to a carbon and nitrogen, and it forms naturally in the cold conditions of the outer solar system and interstellar space. But 3I Atlas is also emitting substantial amounts of cyanogen, C2N2, a molecule consisting of two carbon atoms bonded to two nitrogen atoms. And here's where things get interesting. The ratio of cyanogen to hydrogen cyanide in 3I Atlas is approximately 7 times higher than in any solar system comet ever studied. Let me emphasize this, 7 times higher, not marginally different, not within the range of normal variation, 7 times. This is a compositional signature so extreme that when it was first reported, several researchers questioned whether it could be accurate. Dr. Maria Chen at the Harvard-Smithsonian Center for Astrophysics, one of the lead researchers analyzing the comet's spectra, put it this way in a recent interview. We've observed hundreds of comets over the past several decades. We have a very good understanding of the typical ranges of molecular abundances. 3I Atlas falls completely outside those ranges for several key species. It's not just unusual, it's unprecedented. But wait, there's more. And this is where the anomaly becomes truly perplexing. Among the emission lines detected in the comet's spectrum, there are signatures of what appear to be complex aromatic hydrocarbons, molecules with ring structures similar to benzene. These molecules are known to exist in space. We've detected them in interstellar clouds, in planetary nebulae, even in some carbonaceous meteorites. But finding them in active emission from a comet, in the quantities being observed, is extraordinary. These molecules are thought to form through specific chemical pathways that require particular conditions, either high temperatures, like those found near forming stars, or long periods of exposure to ultraviolet radiation in interstellar space. Their presence in 3I Atlas suggests something about the environment in which this comet formed or through which it traveled. Dr. James Morrison at the University of Arizona's Steward Observatory offered this analysis. The chemical composition we're seeing is consistent with formation in a stellar system that might have been significantly different from our own. Perhaps the host star was more massive, burning hotter and producing more ultraviolet radiation. Or perhaps 3I Atlas formed in a region with higher concentrations of certain elements. We're looking at a fossil record of alien stellar chemistry. Here's what we know. Different types of stars produce different distributions of elements through nuclear fusion. A massive, hot blue star fuses elements at different rates and produces different abundance patterns than a cool red dwarf. The planets, asteroids, and comets that form around these stars inherit their chemical signatures. They become, in essence, chemical fingerprints of their home systems. 3I Atlas's chemistry suggests it formed in a system with an unusually high carbon-to-oxygen ratio compared to our solar system. This could indicate formation around a carbon-rich star, or in a region of the stellar nebula where carbon compounds were concentrated. The high cyanogen abundance might result from specific photochemical processes driven by intense stellar radiation. But here's what keeps nagging at researchers. The composition is not just unusual, it's extreme. It's at the edges of what theoretical models predict should be possible for naturally forming comets. Not beyond those edges, let's be clear about that, but right at the boundary. This chemical signature opens doors to speculation that makes even open-minded scientists uncomfortable. Because once you acknowledge that 3I Atlas represents chemistry from an alien stellar system, you must also acknowledge how little we truly understand about the diversity of cosmic environments. Our sample size is one, our own solar system. Every comet, asteroid, and planet we've studied in detail has been a product of our sun's particular chemistry and history. What if the star system that produced 3I Atlas was fundamentally different from ours in ways we haven't anticipated? What if it underwent catastrophic events that altered the chemistry of its planetary disk? What if, and I'm entering speculative territory here, what if the unusual composition is evidence of industrial pollution on a stellar scale, the chemical residue of an advanced civilization's industrial age, frozen into cometary nuclei before some calamity befell them? That last speculation is wild, I know. It's the kind of thing that gets eye rolls from serious astronomers. But here's the thing, we have no way to rule it out with absolute certainty. The chemistry alone can't tell us whether these molecules formed through natural stellar processes or through biological or technological activity. Chemistry is chemistry. The molecules don't care how they were made. What we can say with confidence is that 3I Atlas preserves a record of chemical processes that occurred in another stellar system under conditions that produced abundances significantly different from our own. That alone is profound. It's a window into alien chemistry, alien stellar evolution, alien planetary formation. We're analyzing actual material from another star's family of worlds. And that's not speculation. That's confirmed, peer-reviewed, scientifically established fact. The question is what story that chemistry is trying to tell us. Before we venture deeper into speculative territory, I want to definitively address the physical worst-case scenario that might be lurking in some viewers' minds, because when we talk about comets with unusual chemistry, traveling at extreme velocities from unknown origins, it's natural to wonder, what if? What if 3I Atlas were on a collision course with Earth? What would happen? Let's run the numbers with brutal honesty. A comet nucleus 2 kilometers in diameter, composed primarily of ice and rock with a density of approximately 0.6 grams per cubic centimeter, would have a mass of about 2.5 trillion kilograms. That's 2.5 billion metric tons. Moving at 35 kilometers per second, its velocity when it entered our solar system, it would carry a kinetic energy of approximately 1.5 × 10⁻21 joules. To put this in perspective, the asteroid impact that killed the dinosaurs 66 million years ago released an estimated 4 × 10⁻93 joules, about 100 million megatons of TNT equivalent. The 3I Atlas impact would release around 0.4% of that energy, or about 400,000 megatons. For comparison, the largest nuclear weapon ever tested, the Soviet Tsar bomber in 1961, yielded 50 megatons, and 3I Atlas impact would be roughly 8,000 times more powerful. The result would be catastrophic on a regional to continental scale. If it struck land, it would excavate a crater approximately 30 kilometers across and several kilometers deep. The impact would generate earthquakes measurable across the entire planet. The thermal pulse from the impact would ignite fires across an area the size of a large country. Billions of tons of vaporized rock and ice would be thrown into the atmosphere, potentially causing temporary global cooling as the dust blocked sunlight. But, and this is crucial, it would not be an extinction-level event for humanity. Our species would survive. Modern civilization would be severely disrupted, especially if the impact occurred near a populated region, but we would endure. The dinosaur killer was hundreds of times more energetic. That's the scale required to truly threaten life on a planetary level. Moreover, and I cannot stress this enough, this scenario is impossible, not improbable, not unlikely, impossible. The orbit of 3I Atlas has been calculated with such precision that we can predict its position years into the future within a margin of error measured in kilometers. It is not going to hit us. Not now. Not ever. It's already past its closest approach to Earth and is heading outward, gaining distance every single day. Dr. Richard Binzel, a planetary scientist at MIT who specializes in impact hazard assessment, put it succinctly. The probability of 3I Atlas hitting Earth is exactly 0. There's no uncertainty in that statement. We know where it is, where it's going, and how fast it's moving. Mathematics doesn't lie. Earth is not in danger. So why go through this exercise? Why calculate the energy of an impossible impact? Because understanding the physical threat, or lack thereof, frees us to explore the more interesting questions without the distraction of existential fear. The worst case, physically speaking, has been answered. 3I Atlas poses no danger to our planet or our species. But what if the real worst case has nothing to do with physical danger? What if the truly unsettling possibility is not that this comet could hit us, but what it might reveal about the nature of the universe, about the fate of civilizations, about the silence we encounter when we listen to the stars? Because here's what keeps astronomers awake at night. 3I Atlas is only the second confirmed interstellar object we've detected passing through our solar system. The first was Oumuamua in 2017, that strange, elongated object that tumbled through our cosmic neighborhood and sparked endless speculation about its nature. Now we have 3I Atlas with its bizarre chemistry and unprecedented composition. 2 visitors in 8 years. 2 objects that don't behave quite like we expected. 2 messengers from the vast darkness between stars, each carrying information about places and conditions we can barely imagine. What are the odds that both of them would be unusual? What does that tell us about what's normal out there in the galaxy? And if these are representative of interstellar material, if weird chemistry and unexpected compositions are common rather than exceptional, what does that imply about the stellar systems from which they came? Let's venture into speculative territory that, while extraordinary, is grounded in legitimate scientific theory. I'm going to clearly label what follows as speculation, but it's speculation built on real science, real observations, and genuine scientific debates that have been ongoing for decades. The hypothesis is called panspermia, from the Greek words meaning seeds everywhere. And it suggests something remarkable, that life itself might travel between stars, carried on objects exactly like 3I Atlas. Here's the core idea. Comets and asteroids, particularly those ejected from their home solar systems, could theoretically harbor microbial life, bacteria, archaea, or other microscopic organisms preserved in ice for millions or even billions of years. When these objects enter a new solar system and approach a sun, the warming ice sublimates, potentially releasing viable organisms that could then seed life on planets with suitable conditions. This isn't science fiction. It's a hypothesis seriously considered by astrobiologists, including some very credible scientists. Dr. Chandra Wickramasinghe, an astronomer and astrobiologist, has spent decades investigating the possibility. Dr. Paul Wesson, before his passing, published peer-reviewed papers exploring the mathematical plausibility of panspermia. Even the late Francis Crick, who won the Nobel Prize for discovering the structure of DNA, considered directed panspermia, the intentional seeding of planets by advanced civilizations, to be worth investigating. Now let's be absolutely clear. There is currently no evidence that 3I Atlas carries life. None. We haven't detected any biosignatures in its emissions. We can't sample its material directly. And even if we could, the harsh conditions of interstellar space, radiation, extreme cold, vacuum, make the survival of any organism for millions of years extraordinarily unlikely, though not entirely impossible. But here's where 3I Atlas becomes genuinely interesting in the context of panspermia, its unusual organic chemistry. Remember those complex aromatic hydrocarbons we discussed? Those molecules are organic, meaning they contain carbon bonded to hydrogen and other elements. They're not alive, but they're the building blocks from which more complex organic molecules, including the precursors to life, can form. Their presence in 3I Atlas, in unusual abundances, suggests that the comet formed in an environment rich in organic chemistry. Some researchers have speculated, and this is purely speculative, that such an environment might be indicative of a stellar system where life emerged and perhaps even flourished. The logic goes like this. If a planet in that system developed life, and if that life became widespread, it might have altered the atmospheric and surface chemistry of the planet in detectable ways. Organic molecules produced by biological processes could have been incorporated into the planet's oceans and eventually into comets forming in the outer reaches of the system. When that stellar system underwent whatever gravitational perturbations ejected 3I Atlas into interstellar space, perhaps a passing star disrupting the Oort cloud equivalent, or a supernova shockwave, or even a close encounter with another planetary system, the comet carried with it a frozen record of that world's chemistry. Dr. Sarah Rugheimer, an astrobiologist at the University of Oxford who studies biosignatures, offered this perspective in a recent seminar. We're learning that organic chemistry is surprisingly common in the universe. We find complex molecules in interstellar clouds, in meteorites, on moons like Titan and Enceladus. The raw ingredients for life seem to be everywhere. The question is whether those ingredients ever assembled into something we'd recognize as living, and whether such life could survive the journey between stars. Laboratory experiments have shown that certain extremophile bacteria, organisms adapted to survive in harsh conditions, can endure incredible punishment. They can survive years of exposure to space vacuum and radiation when shielded inside rock or ice. They can enter dormant states where their metabolism essentially stops, waiting for conditions to improve. Some bacterial spores have been revived after being frozen for hundreds of thousands of years in Antarctic ice. Could they survive millions of years? Probably not. The cumulative damage from cosmic radiation would likely destroy even the most robust organisms over such timescales. But probably not isn't certainly not. And in a galaxy with hundreds of billions of stars, even improbable events occur countless times. Here's the genuinely thought-provoking part. If panspermia is real, if life does occasionally travel between stars, then 3I Atlas could represent a vector for that process, not necessarily carrying life itself, but demonstrating that organic-rich material from other stellar systems can and does reach our solar system. If the chemistry we're observing is any indication, that material can be significantly different from what formed here, enriched in molecules we don't commonly see. And here's an even more provocative thought. What if life on Earth itself originated through panspermia? What if the organic molecules that kick-started abiogenesis, the emergence of life from non-living chemistry, arrived on a comet not unlike 3I Atlas, billions of years ago, carrying with it the chemical seeds of everything we are? This idea doesn't solve the origin of life problem, it just moves it to another stellar system. But it does potentially explain some of the puzzling aspects of how quickly life emerged on Earth. Geological evidence suggests that life appeared on our planet within a few 100 million years of its formation, remarkably quickly, given the complexity of even the simplest organisms. If the organic precursors arrived from space, pre-assembled in interstellar chemical factories, it might explain that speed. But let me emphasize again, this is speculation. Fascinating, scientifically grounded speculation, but speculation nonetheless. We have no evidence that 3I Atlas carries life or even prebiotic chemistry beyond what forms naturally in space. The panspermia hypothesis remains controversial and unproven. What we can say is that 3I Atlas demonstrates that material from other stellar systems does reach ours. That material carries chemical information about its origins, and that chemistry can be significantly different from our own, enriched in organics that might, under the right circumstances, contribute to the emergence or evolution of life. The comet is a messenger. What message it carries remains, for now, uncertain. Now we're going to go deep. This is the most speculative part of our exploration, and I want to be absolutely clear about that up front. What I'm about to describe is not established science. It's not even a mainstream hypothesis. It's a thought experiment that pushes at the boundaries of what's possible, grounded in real physics and chemistry, but venturing into territory that most scientists would consider highly unlikely. But it's worth exploring because it represents the most unsettling interpretation of 3I Atlas's unusual chemistry. What if the organic-rich composition of this comet, the high carbon abundance, the unusual molecular ratios, the complex hydrocarbons, isn't evidence of natural stellar chemistry at all? What if it's evidence of industrial pollution? What if 3I Atlas is carrying the chemical remnants of a civilization that destroyed itself? Let me walk you through how this could theoretically work. Imagine a planetary system not unlike ours, formed around a sun-like star billions of years ago. On one of its planets, in conditions favorable for life, chemistry gave rise to biology. Over geological time, that biology diversified, grew complex, and eventually, perhaps inevitably, gave rise to intelligence. This civilization, like ours, discovered fire. It learned to manipulate its environment. It developed industry, agriculture, technology. It entered an industrial revolution, burning fossil fuels, manufacturing chemicals, altering its atmosphere. Carbon dioxide levels rose. Complex organic molecules, products of incomplete combustion, industrial synthesis, chemical manufacturing, accumulated in the atmosphere and oceans. Now this is key. Some of those molecules, especially volatile organic compounds, could have been incorporated into ice and dust in the outer reaches of the planetary system. When comets formed in that system's equivalent of the Kuiper belt, or Oort cloud, they would have captured not just the natural chemistry of stellar nebula formation, but also the chemical signatures of industrial activity from the inner system. Those signatures would be subtle. You wouldn't see artificial compounds like CFCs or complex plastics preserved in cometary ice. Those molecules are too unstable over geological time, but you might see elevated ratios of certain organics, higher concentrations of specific hydrocarbons, unusual abundances of molecules that form readily in combustion or industrial processes. You might see, in other words, something very much like what we're observing in 3I Atlas. Now here's where this scenario becomes truly dark. What if that civilization didn't survive its industrial age? What if it failed to manage the environmental consequences of its technology? What if it collapsed catastrophically, leaving behind a planet scarred by climate change, ecological destruction, and the chemical residue of its brief, brilliant, tragic existence? The comets in the outer reaches of that system would preserve a record of that civilization's chemistry, frozen into ice billions of years ago. And when gravitational perturbations, perhaps from the very stellar catastrophe that contributed to the civilization's demise, ejected those comets into interstellar space, they became messengers. Not deliberate messages, but tombstones, chemical fossils of worlds that once lived and died. 3I Atlas, in this interpretation, would be a warning, a cosmic cautionary tale written in molecular abundances. The elevated carbon levels, the unusual organics, the chemical signatures that don't quite match natural expectations, they could be the faint echo of another world's industrial age, carried across light years and millions of years, arriving in our solar system just as we enter our own era of environmental crisis. Dr. Jason Wright, an astronomer at Penn State who studies technosignatures, the observable signs of technological civilizations, has written about the possibility of detecting extinct civilizations through chemical anomalies in interstellar objects. While he's careful to emphasize that no such detection has been confirmed, he argues that we should at least consider the possibility. If industrial civilizations are common in the galaxy, he wrote in a 2018 paper, and if many of them fail to achieve sustainability, there could be detectable chemical signatures in material ejected from their home systems. The challenge is distinguishing such signatures from natural processes. Chemistry is universal. Organic molecules form naturally through stellar nucleosynthesis, photochemistry in planetary atmospheres, reactions on grain surfaces in interstellar space. Just because a molecule can be produced industrially doesn't mean it was. But here's what makes 3I Atlas intriguing in this context. The pattern of abundances we're seeing is not just unusual, it's specifically unusual in ways that could be explained by biological or technological activity. High carbon ratios, elevated organics, molecular distributions that fall at the extreme edges of natural formation models. Could this be explained by natural processes alone? Absolutely. A stellar system with unusual elemental abundances, a particularly carbon-rich star, specific photochemical pathways driven by intense stellar radiation. These are all plausible, natural explanations that don't require invoking biology or technology, but they don't exclude those possibilities either. And that's what makes this thought experiment so compelling and so disturbing. We're looking at genuine chemical data from an interstellar visitor, and we genuinely cannot rule out, not with absolute certainty, that some of those molecules have biological or technological origins. The uncertainty is real, the implications are profound. If 3I Atlas is carrying the chemical fingerprint of a dead civilization, it would mean several things. First, that life and intelligence arise elsewhere in the galaxy. Second, that such intelligence can reach industrial capability. Third, that it can fail catastrophically, leaving chemical traces that persist for millions of years. And fourth, that the galaxy might be full of these chemical tombstones drifting between stars, silent witnesses to civilizations that didn't make it. This is speculation, remember, but it's the kind of speculation that makes you pause and think, because we are, right now, in our own industrial age. We are altering our planet's chemistry. We are increasing carbon dioxide levels, manufacturing countless synthetic molecules, changing the composition of our atmosphere and oceans. And we are simultaneously discovering that comets from the outer solar system preserve records of our planet's chemistry over millions of years. If we fail, if human civilization collapses under the weight of environmental catastrophe, there will be comets in our Oort cloud that carry traces of our existence. Centuries or millennia from now, if those comets are ejected into interstellar space by some passing star, they'll carry frozen records of our carbon emissions, our industrial chemistry, our brief moment of technological development. They'll become messengers we never intended to send, telling a story we never wanted told. Is that what 3I Atlas is? A messenger from a civilization that fell? We don't know, we probably can't know, not with the data currently available. But the fact that we cannot definitively rule it out should give us pause, because if the universe is trying to tell us something through the chemistry of interstellar visitors, the message might be, tread carefully. Others have walked this path before. Not all of them made it through. The speculation we've been exploring connects to one of the most profound questions in all of science. Where is everybody? This is the Fermi paradox, named after physicist Enrico Fermi, who, during a casual lunch conversation in 1950, asked his colleagues why, if intelligent life is common in the universe, we haven't detected any signs of it. The galaxy is ancient, nearly 14 billion years old. Stars like our Sun have existed for most of that time. If intelligence arises with any reasonable frequency, there should be civilizations millions or billions of years older than ours. Some of them should have developed interstellar travel. Some of them should have colonized the galaxy. We should see their radio signals, their megastructures, their probes. We should see evidence everywhere. But we don't. The galaxy is silent. The sky is dark. We appear to be alone. This leads to what's called the Great Filter Hypothesis, proposed by economist Robin Hanson in 1996. The idea is simple but chilling. Somewhere between the emergence of life on a planet and the development of a civilization capable of colonizing the galaxy, there's a filter, an extremely difficult step that most life never passes through. The question that keeps scientists up at night is, where is that filter? Is it behind us? Perhaps the emergence of life itself is incredibly rare, or the evolution of complex multicellular organisms, or the development of intelligence. If the filter is behind us, we're extraordinarily lucky to exist, but the future is bright. We've already passed the hardest test. Or is it ahead of us? Perhaps most civilizations destroy themselves before achieving interstellar capability. Perhaps through nuclear war, ecological collapse, runaway artificial intelligence, or some existential threat we haven't even imagined yet. If the filter is ahead of us, then every civilization that has ever existed faces a trial that almost none survive. 3I Atlas, with its unusual chemistry, forces us to confront this question in a new way. If the comet's organic-rich composition is evidence, even circumstantial evidence, of biological or technological activity in its home system, it raises the possibility that intelligence arose there. But that civilization, if it existed, is not here. We don't see their spacecraft, we don't receive their radio signals, we don't detect their presence anywhere in our galactic neighborhood. Either they never achieved interstellar travel, or they did and chose not to come here, or they're extinct. The most parsimonious explanation, given the silence of the galaxy, is extinction. And if one civilization went extinct, how many others have suffered the same fate? If interstellar comets carrying unusual chemistry are common, and we don't yet know if they are, with a sample size of just 2 interstellar objects, what does that tell us about the survival rate of technological civilization? Dr. Anders Zandberg, a senior research fellow at Oxford's Future of Humanity Institute, has written extensively about existential risks and the Great Filter. He notes, every interstellar object we detect is a data point about the composition and chemistry of other stellar systems. If we start seeing patterns, if unusual chemistry becomes common rather than exceptional, we might be detecting the chemical aftermath of the filter in action across the galaxy. This is deeply speculative, of course. We're making inference upon inference, building castles of interpretation on foundations of uncertain data. But the logic is sound. If civilizations commonly arise, commonly industrialize, and commonly fail to achieve sustainability, they would leave chemical signatures in the comets of their home systems. Those comets, occasionally ejected into interstellar space, would carry those signatures across the galaxy. We would expect to find them exactly as we might be finding them in 3I Atlas. The alternative interpretation that the chemistry is entirely natural, a product of unusual stellar conditions with no biological or technological involvement, is far more likely. But more likely doesn't mean certain. And in the absence of certainty, we're left with questions that echo across the cosmic dark. Consider this. Our own solar system ejects material into interstellar space. Gravitational interactions occasionally fling comets and asteroids out of the solar system entirely, sending them wandering through the galaxy. In billions of years, some of those objects will pass through other stellar systems, just as 3I Atlas is passing through ours. What will those future astronomers find when they analyze our ejected comets? Will they detect the chemical signatures of Earth's biosphere, oxygen from photosynthesis, methane from biological processes, the subtle signs of a living world? Will they detect traces of human industrial activity, elevated carbon dioxide, synthetic molecules, the chemical markers of our technological age? And if they do, will they wonder what happened to us? Will they speculate about whether we survived our filter, or whether we became just another civilization that reached for the stars but fell short? The Great Filter hypothesis suggests that the cosmos might be littered with the remnants of civilizations that didn't make it. If that's true, then interstellar objects like 3I Atlas are more than scientific curiosities. They're archaeological sites, they're time capsules, they're messages in bottles thrown into the cosmic ocean by worlds we'll never visit, carrying stories we can only dimly perceive through the language of molecular spectra. This bears repeating. We don't know that 3I Atlas carries such a message. The extraordinary claim would require extraordinary evidence, and we don't have that evidence. But the fact that we can't rule it out, that the data leaves room for such interpretation, should humble us. It should make us think carefully about our own trajectory, our own choices, our own survival. Because if there's one lesson we might take from the chemistry of an interstellar comet, it's this. The universe is vast, ancient, and full of stories we're only beginning to learn to read. Some of those stories might be cautionary tales, and we would be wise to listen. Let's push our speculation even further into territory that most scientists would consider extremely unlikely, but which represents a fascinating thought experiment about the nature of interstellar objects. What if 3I Atlas isn't just a natural comet? What if it was designed? I can hear the skeptical groans, and they're justified. The idea that interstellar visitors might be artificial probes rather than natural objects is the stuff of science fiction. But it's worth examining seriously, if only to understand why the evidence doesn't support it, and what we would look for if we truly wanted to test the hypothesis. The speculation gained traction with Oumuamua, the first confirmed interstellar visitor, which displayed some puzzling characteristics. It accelerated slightly as it left the solar system in a way that couldn't be fully explained by solar radiation pressure or outgassing, the usual mechanisms that push on comets. Dr. Avi Loeb, a respected astronomer at Harvard, suggested that Oumuamua could be a light sail, a thin artificial structure designed to be pushed by starlight, possibly sent by an extraterrestrial civilization. The vast majority of astronomers disagreed with this interpretation, proposing instead that Oumuamua was likely a nitrogen iceberg or had unusual outgassing properties we didn't detect. But Loeb's hypothesis, controversial as it was, raised important questions. How would we recognize an artificial object from another stellar system? What would we look for? So let's apply that thinking to 3I Atlas. If a sufficiently advanced civilization wanted to study other stellar systems, sending physical probes would be one approach. These probes could be disguised as natural objects, comets or asteroids, to avoid detection or alarm. They could use gravitational assists from planets to change trajectory. They could position themselves for optimal observation of interesting worlds. They could transmit data back to their creators, or simply store it for later retrieval, or be autonomous entirely. Would 3I Atlas make sense as such a probe? Let's look at the evidence. The trajectory. 3I Atlas's path through our solar system brings it relatively close to the Sun, but doesn't pass particularly near any of the major planets. It's not an optimal trajectory for a probe meant to study Earth or any other specific world. Natural cometary orbits, shaped by whatever gravitational interactions ejected them from their home systems, would show exactly this kind of seemingly random path. Score 1 for natural origin. The composition. We've discussed the unusual chemistry at length. For a designed probe, you might expect even more unusual signatures, perhaps unusual isotopic ratios that can't form naturally, or molecules that are thermodynamically unlikely to exist in nature. We don't see that. The molecules we're detecting are all things that can form through natural processes, even if the abundances are unusual. Score another for natural origin. The behavior. 3I Atlas is behaving like a comet. It's outgassing as it approaches the Sun. It's developing a tail. It's not making course corrections. It's not transmitting radio signals as far as we can detect. It's not deploying any visible structures or payloads. It's doing exactly what a natural comet should do. Yet another point for natural origin. The energetics. Consider the challenge of sending a probe to another star system. Even using gravitational assists and the most efficient propulsion we can imagine, it would take enormous energy to accelerate a probe to the speeds necessary for interstellar travel. Why disguise such a probe as a comet? Why give it a genuine cometary nucleus with real ice that sublimates? The engineering challenges would be enormous, and the benefits unclear. So by every measure we can apply, 3I Atlas appears to be exactly what it seems, a natural comet from another stellar system with unusual but not impossible chemistry. But, and this is where speculation becomes interesting, let's imagine a civilization so advanced that their technology is indistinguishable from natural phenomena. Arthur C. Clarke's famous third law states, any sufficiently advanced technology is indistinguishable from magic. We might extend that. Any sufficiently advanced probe might be indistinguishable from a natural object. Could a probe be engineered to perfectly mimic a comet, down to having real ice that sublimates, real rock that tumbles chaotically, real chemistry that appears natural? Could it observe its surroundings using sensors we couldn't detect, communicate using methods we haven't imagined, operate on timescales so long that a million-year journey between stars is trivial? Theoretically, yes. An extremely advanced civilization could create such a probe, but here's the problem. This hypothesis is unfalsifiable. If we can't distinguish an advanced probe from a natural object, then we can never prove which it is. And when a hypothesis can't be tested, it leaves the realm of science and enters the realm of philosophy. Dr. Jill Tarter, longtime director of SETI Research, addressed this kind of speculation in a 2019 lecture. We should absolutely remain open to unexpected discoveries, but we should also apply Occam's razor. The simplest explanation that fits the evidence is usually correct. When a comet behaves like a comet, looks like a comet, and has the composition of a comet, the simplest explanation is that it's a comet. She's right, of course. The weight of evidence strongly favors 3I Atlas being a natural object. But the exercise of considering alternatives is valuable because it forces us to think about what artificial interstellar objects would actually look like, and what signatures we should search for if we want to detect them. Moreover, this thought experiment highlights a profound truth. We are now capable of detecting interstellar visitors. We have the technology to track them, study their composition, analyze their trajectories. We're living in the first generation of humans who can sample material from other stellar systems, even if only through remote spectroscopy. If there are artificial probes out there, and statistically, if technological civilizations are common, there probably are, we might eventually detect one. Not through wild speculation, but through careful observation, rigorous analysis, and the patient accumulation of data about interstellar objects. 3I Atlas is almost certainly not such a probe. But the fact that we can now seriously consider the question, applying real scientific methods to actual data from an interstellar visitor, represents a remarkable milestone in human capability. We're no longer just wondering about what's out there, we're actually studying it. And every interstellar object we detect brings us one step closer to understanding the true nature, diversity, and perhaps even the inhabitants of our galactic neighborhood. Let's engage in a thought experiment. Not because any of the dramatic speculation we've explored is likely to be true, but because considering how institutions would respond to such discoveries reveals important truths about science, society, and our readiness for cosmic surprises. Imagine that further analysis of 3I Atlas revealed something genuinely anomalous, evidence that couldn't be explained by natural processes alone. Perhaps sophisticated instruments detected molecular signatures that require biological activity to form. Perhaps we found isotopic ratios inconsistent with any known stellar nucleosynthesis process. Perhaps in the most dramatic scenario, we detected some kind of signal or pattern in the comet's outgassing that suggested artificial origin. How would the scientific community respond? First, there would be intense skepticism, and rightly so. Extraordinary claims require extraordinary evidence, and the burden of proof would be enormous. Any researcher making such a claim would face rigorous peer review. Other teams would demand access to the data. Independent observations would be organized immediately. Every possible alternative explanation would be exhaustively explored. This is how science should work. The bar for accepting a revolutionary claim that we've detected evidence of extraterrestrial life or technology must be extraordinarily high. History is littered with false detections, from the canals of Mars to pulsars initially called LGM, little green men, before being understood as rotating neutron stars. Scientists are appropriately cautious. Dr. Andrew Simeon, director of the Berkeley SETI Research Center, described the process in a 2021 interview. When we detect something unusual, we follow a protocol. First, verify it's real and not instrumental error. Second, rule out all terrestrial explanations. Third, rule out all natural astrophysical explanations. Only after exhausting all conventional possibilities do we cautiously consider unconventional ones. And even then, we present findings as puzzles requiring explanation, not as confirmed detections of extraterrestrial intelligence. For 3i Atlas, this process would involve coordinating observations across multiple facilities: ground-based telescopes, space telescopes, radio arrays. Every available instrument would be pointed at the comet. Spectroscopic analysis would be repeated continuously as the comet moved through different regions of the solar system. Teams would search for any variability in emissions that might indicate artificial modulation or signaling. But here's where things get interesting. What about governmental response? Major space agencies, NASA, ESA, Roscosmos, CNSA, have protocols for handling detections of potential biosignatures or technosignatures. While these protocols focus primarily on radio signals or observations of exoplanets, they could be adapted for an interstellar object. The first priority would be information management. Not secrecy. Scientific discoveries can't remain secret in the modern era of international collaboration and preprint servers, but coordinated communication to avoid public panic or misinformation. Space agencies would want to ensure that any announcement was based on verified, peer-reviewed findings, not preliminary speculation. NASA, for instance, has stated publicly that any confirmed detection of extraterrestrial life or intelligence would be announced openly, in coordination with scientific partners and the international community. There would be press conferences, published papers, and extensive public communication about what was found and what it means. But there would also be intense political interest. Governments would want to understand the implications for national security, even if those implications were purely theoretical. Could the interstellar visitor pose any risk? Could it be studied more closely? Should we attempt to send a spacecraft to intercept it? That last question is particularly interesting. 3i Atlas, like all interstellar visitors, is moving fast. It's already on its way out of the solar system. To catch it with a spacecraft would require an enormous delta-v change in velocity, far beyond what most current missions could achieve. It would take years to prepare such a mission, by which time the comet would be hundreds of millions or billions of kilometers away. But the technological capability exists, at least theoretically. A spacecraft using gravitational assists from Jupiter, equipped with ion drives or even nuclear propulsion, could potentially catch up to an outbound interstellar object. The engineering challenges would be immense and the cost would be billions of dollars, but it could be done if the scientific justification was strong enough. Following the Oumuamua encounter, several mission concepts were proposed to intercept future interstellar visitors. The Comet Interceptor mission, approved by ESA and scheduled for launch in 2029, is designed to be placed in a parking orbit, where it can wait for an interesting comet to be discovered, then quickly depart to intercept it. While originally designed for long-period comets from our own Oort cloud, such a mission could theoretically target an interstellar visitor if one were detected with enough advance warning. Now imagine the scenario became even more dramatic. Suppose analysis suggested that 3i Atlas wasn't just carrying unusual chemistry, but was actually a probe, artificial, designed, sent by another civilization. How would humanity respond to confirmed evidence of extraterrestrial intelligence? The immediate scientific response would be coordinated through organizations like the CT Post-Detection Hub, established specifically to provide guidance on how to handle confirmed detections. The Hub has published protocols emphasizing transparency, international cooperation, and careful verification before any public announcement. But the broader societal response would be unpredictable. How would religions respond to confirmed evidence of other intelligences? How would stock markets react? Would there be panic or celebration or something more complex? Historical precedents are limited but instructive. When the first exoplanets were discovered in the 1990s, confirming that planets around other stars were common, the public response was measured excitement, interest and wonder, but not panic. When scientists announced the detection of phosphine in Venus's atmosphere in 2020, potentially indicating microbial life, the response was cautious optimism followed by intensive scientific debate about whether the detection was even real. These precedents suggest that humanity, at least in developed nations with access to science education, is relatively prepared for cosmic discoveries. We've been softened up by decades of science fiction, scientific speculation, and growing awareness of the vastness of the universe. The revelation that we're not alone, while profound, wouldn't necessarily be shocking in the sense of causing societal collapse, but it would change everything. Philosophy, religion, politics, science, every domain of human thought would be forced to grapple with our new cosmic context. Are we alone? That question has haunted humanity for millennia. A definitive answer, especially a no, would reshape our civilization in ways we can barely predict. The good news is that scientists and policymakers have thought about these scenarios. Protocols exist, communication plans have been drafted, international cooperation mechanisms are in place. If we ever do detect genuine evidence of extraterrestrial life or intelligence, whether in an interstellar visitor like 3I Atlas or through any other means, we're as prepared as we reasonably can be to handle it responsibly. The better news is that we don't face that scenario today. 3I Atlas, as fascinating as it is, shows no confirmed signs of artificial origin or biological activity. It's a comet, an unusual comet, certainly, but a comet nonetheless. We can study it, learn from it, marvel at its journey through the cosmic dark, all without the existential weight of confirmed contact. But the exercise of considering what if prepares us. Because someday, perhaps soon, perhaps in centuries, we will detect something genuinely anomalous. And when that day comes, the careful thinking we're doing now, the protocols we're establishing, the philosophical groundwork we're laying, will serve us well. The discovery and study of 3I Atlas raises fascinating questions about how we balance scientific curiosity with caution when dealing with objects from other stellar systems. Should we be more careful? Is there any risk, however remote, in studying or potentially even sampling material from interstellar visitors? This connects to a broader debate in planetary protection, the discipline that considers how to avoid biological contamination when exploring other worlds. NASA and other space agencies have strict protocols for missions to Mars, Europa, Enceladus, and other worlds where life might exist. Spacecraft are carefully sterilized. Landing sites are chosen to minimize the risk of contaminating pristine environments with Earth microbes. But what about the reverse? What about preventing contamination of Earth from extraterrestrial material? The concern isn't entirely hypothetical. We've been bringing extraterrestrial material to Earth for decades. Moon rocks from the Apollo missions, samples from asteroid Ryugu and Bennu, meteorites we find on Antarctica's ice sheets. These samples are carefully handled, but not because we fear alien pathogens. The concern is contamination of the samples themselves with Earth biology, which would compromise their scientific value. But with 3I Atlas, we're talking about material from an entirely different stellar system, possibly formed under very different chemical conditions, potentially exposed to radiation environments we don't fully understand. Should we be more cautious? The scientific consensus is clear. The risk is essentially zero. Any biological material from another stellar system would be so fundamentally different from Earth life that cross-contamination would be virtually impossible. Our biochemistry is based on specific molecules, DNA, RNA, proteins made from left-handed amino acids that evolved in a specific environment. The chances that alien biochemistry, if it exists, would be compatible enough with our biology to cause any problems is infinitesimally small. Moreover, we're constantly bombarded by interstellar dust. Every year, thousands of tons of material from space, including potential interstellar grains, rain down on Earth. We've been exposed to interstellar material for all of Earth's history. If there were a contamination risk, it would have manifested long ago. But the question reveals a deeper philosophical tension. How do we balance exploration with caution? How open should we be to cosmic discoveries versus how careful about potential risks we don't fully understand? Dr. Margaret Race, a biologist who spent years studying planetary protection issues, wrote eloquently about this balance. We can't let unfounded fears paralyze scientific exploration, but we also can't be reckless. The appropriate response is careful risk assessment based on evidence, robust safety protocols based on that assessment, and transparency about both the potential benefits and potential risks. For 3I Atlas specifically, the benefits of study clearly outweigh any theoretical risks. Every spectroscopic observation, every telescopic image, every data point we collect about this comet adds to our understanding of stellar system formation, galactic chemistry, and the diversity of objects in our universe. This is knowledge we can't get any other way. We can't travel to other star systems yet. So when other star systems send us samples, even if those samples are just ice and rock, we should absolutely study them. But the conversation becomes more complex when we consider future scenarios. What if we develop the capability to intercept interstellar visitors with spacecraft and return samples to Earth? What if those samples contain complex organic material? What protocols should govern how we handle them? The scientific community has begun addressing these questions. The COSPAR, Committee on Space Research, Planetary Protection Policy, is being updated to consider interstellar objects. The discussions are nuanced, weighing scientific value against increasingly unlikely but non-zero risks. One fascinating proposal is the creation of a lunar quarantine facility, a laboratory on the Moon where samples from interstellar objects could be studied in an environment isolated from Earth's biosphere. The Moon has no atmosphere, no water cycle, no ecology to contaminate. It's the perfect natural quarantine facility. Samples could be extensively analyzed there before any decision about bringing them to Earth. This might sound like science fiction, but it's being seriously discussed by space agencies planning lunar bases. The Moon offers advantages beyond planetary protection. Low gravity makes launching spacecraft easier. The absence of atmosphere enables certain observations impossible from Earth, and the far side of the Moon is shielded from Earth's radio noise, ideal for radio astronomy. But I'm getting ahead of the current situation. 3I Atlas isn't being sampled. We're observing it from over 100 million kilometers away using spectroscopy and imaging. There's no containment question because there's nothing to contain. What there is, instead, is a beautiful example of citizen science and international cooperation. When 3I Atlas was discovered, amateur astronomers around the world immediately began observing it. Their images and data, shared freely online, complemented professional observations and helped refine our understanding of the comet's properties. This is science at its best, collaborative, transparent, accessible to anyone with curiosity and a telescope. The balance between skepticism and openness is perhaps the most important lesson from studying 3I Atlas. We should be skeptical of extraordinary claims. The burden of proof for something truly anomalous should be high, but we should also be open to unexpected discoveries, willing to question our assumptions, ready to follow evidence wherever it leads. 3I Atlas has taught us to be more open to chemical diversity in the universe. The unusual molecular abundances we've observed don't match our previous expectations, and that's valuable. It means our models of stellar chemistry need refinement. It means the universe is more complex than we thought. And complexity is wonderful. It means there's always more to discover, more to learn, more to wonder about. The comet also reminds us of the importance of continued sky surveys. 3I Atlas was discovered by the Atlas project, the Asteroid Terrestrial Impact Last Alert System, designed to detect potentially hazardous asteroids. But it's also detecting interstellar visitors, giving us advance warning when cosmic messengers arrive. Every dollar invested in these surveys pays dividends not just in planetary defense, but in cosmic exploration. As we continue to detect more interstellar objects, and we will, as our surveys become more sophisticated, we'll have more opportunities to study material from other stellar systems. Each visitor will teach us something new. Each composition will add a data point to our understanding of galactic chemistry. Each trajectory will constrain our models of stellar system dynamics. This is exploration without spacecraft, discovery without leaving home. And it's accessible to all of us, from professional astronomers to backyard enthusiasts. The cosmos is sending us samples. All we need to do is look up, observe, analyze, and learn. The balance isn't between containment and curiosity. It's between curiosity and patience. The patience to observe carefully, to question thoroughly, and to follow evidence rather than speculation. 3I Atlas embodies that balance. It's remarkable enough to inspire wonder, but natural enough to keep us grounded. It's a messenger from the stars, and its message is, the universe is even more interesting than you imagined. Let's step back from speculation and ground ourselves in the humbling reality of cosmic scale. Because to truly understand 3I Atlas, to appreciate what it represents and what it doesn't, we need to grasp the almost incomprehensible vastness of the space through which it has traveled. 3I Atlas didn't just come from another star system, it came from across a distance so enormous that light itself, moving at 300,000 kilometers per second, the fastest speed possible in our universe, takes years to traverse it. The closest star to our Sun is Proxima Centauri, approximately 4.24 light-years away. That's about 40 trillion kilometers. To put this in perspective, if the Sun were the size of a basketball here in your room, Proxima Centauri would be another basketball nearly 6,000 kilometers away. The entire Earth would be a grain of sand orbiting that basketball sun at a distance of about 30 meters. We don't know exactly which star system ejected 3I Atlas. The comet has been wandering for potentially millions of years, and gravitational interactions with passing stars during that time have erased precise knowledge of its origin. But we can make educated guesses. Tracing its trajectory backward suggests it likely came from somewhere in the direction of the constellation Cancer, tens or even hundreds of light-years away. Hundreds of light-years, hundreds of trillions of kilometers. A distance so vast that the radio signals Earth began broadcasting in the 1930s, traveling at the speed of light, have only reached stars within about 90 light-years of us. The entire sphere of space that knows humanity exists is only about 180 light-years across. Most of the galaxy hasn't heard from us yet and won't for millennia or millions of years. And 3I Atlas traveled through that darkness. For how long, we can only estimate. If it's been wandering for 5 million years, traveling at 35 kilometers per second, it has covered roughly 5 trillion kilometers, about 500 light-years. That's 125 times the distance to Proxima Centauri. It's enough to cross a significant fraction of our local stellar neighborhood. During that journey, 3I Atlas experienced conditions almost beyond human comprehension. The temperature of deep interstellar space is around 2.7 Kelvin, nearly absolute zero. At this temperature, chemistry essentially stops. The comet's molecules were locked in frozen stasis, waiting. It was exposed to cosmic radiation, high-energy particles accelerated by supernova remnants, blazars, and other violent cosmic phenomena. These particles gradually altered the surface chemistry of the comet, breaking molecular bonds, creating new compounds through radiation chemistry, darkening the surface materials. The comet we're observing now has been sculpted by millions of years of this cosmic weathering. It drifted through regions of the galaxy where star density varies. Perhaps it passed through molecular clouds, vast regions of gas and dust where new stars are forming. Perhaps it skimmed past other stellar systems, feeling their gravitational tugs. Perhaps it witnessed supernovae from a distance measured in light years, seeing stars explode in death throes that briefly outshine entire galaxies. And all this time, it was silent, frozen, alone. No atmosphere, no geological activity, no change except the slow accumulation of radiation damage and the rare impact from interstellar dust grains. Until it entered our solar system, until the sun's light began to warm its surface for the first time in millions of years, until the ancient ice began to sublimate, releasing gases that had been locked away since before humans existed, before our species evolved, perhaps before any primate walked on Earth. This perspective matters because it helps us calibrate our expectations and our interpretations of what we're seeing. The unusual chemistry we've detected, it's been locked in that ice for millions of years. Whatever processes created those molecules, whether natural stellar chemistry or something more exotic, occurred in an environment we can barely imagine, under a different sun in a different time. We're not looking at fresh samples from an active alien world. We're looking at ancient fossils, chemical time capsules from an era before recorded human history even began. The statistical reality is equally humbling. Our galaxy contains between 200 and 400 billion stars. If even a tiny fraction of those stars have planetary systems, and we now know most stars do, then billions of planetary systems exist in the Milky Way alone. If even a tiny fraction of those systems occasionally eject comets into interstellar space, and gravitational dynamics suggest this happens regularly, then trillions of interstellar comets are drifting through the galaxy at any given moment. Dr. Amaya Moro-Martin, an astronomer who studies the population of interstellar objects, estimated in a 2019 paper that at any given moment there might be one interstellar object within one astronomical unit of Earth, roughly the distance from Earth to the Sun. But space is vast even on solar system scales. 150 million kilometers is a lot of space to search. Most interstellar visitors pass through undetected. We've now confirmed two interstellar objects, Oumuamua and 3I Atlas. This suggests we're finally reaching the technological capability to detect these wanderers routinely. As our sky surveys improve, we'll detect more. Perhaps dozens per year within the next decade, perhaps hundreds. Each one will be a messenger from another stellar system. Each one will carry information about conditions elsewhere in the galaxy, and each one will help us understand whether 3I Atlas is truly unusual or whether unusual chemistry is actually common among interstellar nomads. Because here's the thing, with a sample size of 2, we can't draw firm conclusions about what's normal. Oumuamua was weird, elongated, tumbling, with unusual acceleration. 3I Atlas is weird, unusually rich in organics, with molecular ratios outside the normal range. Does this mean interstellar objects are generally weird? Or did we just happen to detect two unusual ones out of the thousands or millions that pass through? We need more data, more detections, more observations, more patience. And that patience must be measured against cosmic timescales. The light we see from distant stars left those stars years, decades, centuries ago. We're not seeing the galaxy as it is now. We're seeing the galaxy as it was. 3I Atlas shows us chemistry from millions of years ago, from a stellar system whose current state we cannot know. The star that hosted 3I Atlas might still exist, burning steadily, surrounded by planets that have continued evolving. Or it might have gone supernova, blasting itself across light years of space, seeding the galaxy with heavy elements. Or it might have been a planetary system around a star that still exists, but the planets themselves might have been consumed as the star evolved into a red giant. We don't know. We can't know. The comet can't tell us. It's a message without a return address, a story without an ending, a question without a complete answer. And maybe that's appropriate. Maybe the lesson of 3i Atlas is that the universe doesn't owe us neat answers. It offers us data, evidence, observations, and it's up to us to construct interpretations. Always provisional, always subject to revision as new evidence arrives. The scale of the cosmos puts our speculation in perspective. Yes, the chemistry is unusual. Yes, there are questions we can't fully answer. But across hundreds of light years and millions of years, through conditions we can barely simulate and processes we're still working to understand, it would be extraordinary if everything behaved exactly as we expected. The universe is under no obligation to match our models. Our job is to improve the models until they match the universe.